Hello, I am Kim Yuji, a joint MS and PhD student at AmiLab. Today, I'd like to introduce SpatialBot, precise spatial understanding with vision language models, which will be presented at ICRA 2025. I think most students are familiar with VLMs. So VLM consists of image encoder, connector, and LLM model. So when a vision encoder is added to the language model, we can call VLM or multimodal large language models. In recent years, VLMs have achieved impressive performances on general 2D visual tasks like perception, listening, and OCR. You can see here. However, they still struggle with spatial understanding, which is the fundamental task to embodied AI. It is the example of some spatial reasoning. And when with only the RGB images, and we ask, has the gripper touched the leg? And the GPT said, the gripper has touched the leg, visually contact. But I will show the next result, but actually they did not contact. So the authors suggest that comprehending the entire space from a monocular RGB image is the overwhelming for VLMs. So to enhance the spatial understanding, the authors suggest that we need to utilize both RGB and depth images. Integrating this information could effectively enhance the spatial understanding capability of VLMs. This is the example with reasoning with the depth image. Compared to the RGB result, depth help identify whether the gripper is touched or not. So Spatial is the proposed method of this paper, and based on the real depth value, they reasoning like the leg's depth value is here and the gripper depth value is here. So the gripper has not touched the leg. So they show better spatial reasoning result than only RGB inputs. So in this paper, the authors point out that VLMs lack spatial reasoning capabilities and aim to improve them. There are three main challenges for VLMs to help spatial reasoning. And we can call this depth input VLM like RGBD, or we can call it 2.5D VLMs. So the first challenge is that previous VLM models are only trained with RGB images, and they did not see the depth images. And directly inputting this map into the VLM result for performance. Second, a well-designed dataset for training VLM to understand depth is absent. The most popular VLM training dataset did not provide depth maps or depth-related text. Finally, there is a scale inconsistency between indoor and outdoor numerical depths. For example, tasks such as indoor navigation and manipulation requires millimeter level very high precision. But for the outdoor tasks, they demand a broader depth range rather than such high precision. So we need to unify them with some high precision level. To overcome these challenges, the authors introduced the following solutions. First, they propose a SpatialBot model, which the input is the RGB and depth images. And they show promising performance in spatial understanding and local manipulation. Additionally, SpatialBot also shows promising results in general visual recognition. Next, they curate large-scale RGB VQA dataset. Spatial QA and Spatial Bench are for spatial understanding, and Spatial QAE is for robot manipulation task. So the E means embodied. And finally, they propose a carefully designed decimal encoding to preserve all depth information for VRM to use. So the author directly saved the low depth value and feeds them to VRMs. So this is the motivation part, and next we will move to the architecture. Is there any questions so far? So keep going. This is the SpatialBot architecture. The architecture is pretty straightforward. The input is paired of RGB and depth images, and depth is used to guide VRMs in understanding over space. So the architecture looks like this, and it extends the original RGB-based VRM model by incorporating an additional depth encoder. So it's quite nice architecture, I think. And they also suggest depth API. It is some function and get accurate depth information. And their base VRM model is funny, and which comes from the same group of SpatialBot, so they use this. Is all of the architecture. And next is the data securation part. The authors introduce a data set specifically designed for spatial region. So the name is Spatial QA. And they design carefully with three-step QA pipeline to let the VRM train progressively depth information. So the level is 3, and for the low level, they want just VRM to understand depth. And for the middle level, they want to VRM align depth and RGB image and learning their relationship. And for the high level, they use depth for complex reasoning in high level tasks. So in the low level step, the goal is to help VRM to understand depth information. For that, they ask depth value of a specific point like this, and let the VRM describe and infer what may be in the image with only depth map. So this level just one VRM to understand depth. And in the middle level, the goal is to align depth and RGB images and know the relationship between them. So they ask some proximity relationships. It means that which point is closer or further away. So it is some kind of spatial relationship. And they let VRM describe the depth of objects or region. In the high level, the goal is to use depth for complex spatial reasoning tasks, such as counting, enumeration, and determine spatial and positional relationships. In the high level task, VRM can count the object and reasoning about the enumeration. So to summarize, the authors designed the data set to help VRM understand depth information by progressively learning in 3 steps. And they also suggest proper depth encoding for passing depth to the VRMs. The goal of the depth map encoding is to preserve the all depth information for VRM to use. As I mentioned before, there are some challenges for dealing with the depth map information. The main challenge is that there are inconsistencies between indoor and outdoor depth map scale. Indoor scene requires high precision level, but outdoor scene need to not high precision, but larger range of depth value. To serve these, they directly save low depth values using a unified scale and with a wide range of. They directly pass these low values to VNFs and leave subsequent computations to the buffer fitting capabilities of VNFs. So when we want to get the depth map, we can use depth estimation models. And there are two kinds of depth estimation model. First is the relative depth, and second one is the metric depth. And first, for the relative depth model, they only adapt ordinary encoding. So they cannot used for the basic mathematical operations. Because in here, when we get the relative depth information, we need to get some conversion process to get the actual depth. And when this conversion path is used some additional correction factor like here. So the relative depth values does not mean some proportional relationship. So we cannot use these values at the mathematical operations. So in this paper, they use metric depth model for get depth estimation. They use draw depth model as a metric depth estimation models. And it considers both indoor and outdoor scenarios, and also can get accurately estimated metric depths. So the target depth range they want to represent is like this. And for this range, we can use two types of data type. First is Uint 24, and the second one is 3-channel Uint 8. So first, we can directly use some larger range to store these all depth values. They use millimeters as unit directly and also can directly query the required value from the depth map. But there are some uncomfortable points. First, it is not a standard unit format, so it is hard to pass this value directly to the VNFs. So we want to use this 3-channel unit format to some conversion process. And these negative effects are my interpretation. So they designed this 3-channel unit 8 encoding. So they distribute the value across the broad range. So they split all depth range in 3 units. First, like here. Yeah. So the reason they choose this larger unit is that some practical scenario like desktop graphing task typically has a maximum depth of around 1 meter. So they use this unit as a first unit. And when you use a larger unit, would result in the first channel being predominantly zero. And the authors also added multiple layers here to better distinguish between the 3 channels. So they expect that VLMs can easily learn the relationships between their encoding and actual depth value. And in the experiment section, they showed that. So it is the all about the architecture. Is there any questions so far? Okay. And the authors also propose some advanced data set. The name is Spatial QAE for demonstrate the embodied task. So they use real robot arms for it. The task is some similar previously Dong-Hyun showed. They grab object on the table and place them on the target place and when move the robots, they avoid obstacles while moving. So to experiment these spatial QAE scenarios, they fine-tune based on the previous SpatialBot model, and it is work like visual language action model. And on the right, you can see the first step process of picking a layer teacup and place it on the light cupboard. So you can hear they pick this layer cup and move on to this cutting board. And in here, they use cups, and first one is fake printed teacup, and second one is layer teacup. So because we can use depth map, it is easier to distinguish between layer and the printed teacup. And the final data set they propose is the spatial bench. And the other propose not only propose for the training, but also propose some evaluation data sets. So it includes questions based on the spatial relationships, such as touching, reaching, counting, enumeration, and so on. So this is the result on the spatial bench evaluation dataset. They compare their result with the GPT-4. GPT-4 only trained with the RGB images, and when they test, they use RGB and RGB-D, both of them. And in here, depth column means that when we get the only RGB images, and the SpatialBot infer layer depth value at this point. So it is the same as the depth estimation task. So in here, position and existence quality are similar to GPT, and it shows more higher result for spatial information reasoning, such as counting and reaching task. However, it shows poor result for size task, so which need to be more improved. And this is the result on general VRM benchmarks. In here, only these two models, they use RGB and depth joint input because this task consists of counting, existence, and position question, which is the spatial reasoning. And this result show that VRMs are weak at the spatial reasoning, but spatial VAQA training helps without harming general performance. So SpatialBot also show better performance than in the general VRM. This is the last result of the and this is for the robot manipulation in embodiment task. This is the success rate in pick and place of RGB and RGB-D input, and for the embodied task, the depth input showed more superior than the only RGB inputs. It is all the results. So, is there any questions? Okay, so let's summarize the paper. First, the authors propose SpatialBot, which can also be called RGB or 205 VRMs. So they show the promising result in general visual recognition and spatial understanding and robot manipulation. The author first create a large scale RGB-D data sets with 3 levels of task. And they also provide a data set with for training and for evaluation. They also fine-tune and deploy these real models with some carefully designed depth-my encoding, and also shows SpatialBot's result in the embodied task.